Hi you guys, welcome to part 2 of a pair of videos I'm making about how you can use Monte Carlo to explore your risk environment. Please remember that I'm supporting these two videos with a memo and an Excel worksheet that explains my position completely. To see these, just go to stephenpereer.com, click on the research tab, and then track down the Monte Carlo link. I strongly believe that we have two choices here. We can, one, keep complaining about the barriers caused by the data that we don't have at the moment and may never acquire, or we can, two, try something new by using Monte Carlo to model our current circumstances and start learning more about the actual shape and dimensions of the risks in our work environment. Now, as I said in part 1, here's the setting that we want to model. Our initial conditions begin when we expose both our sensor and our calibration standard to the same physical conditions to compare their responses. It doesn't matter if these conditions involve temperature, mass, pressure, whatever. Then we want to model the consequences if we found out later that this calibration standard might have been out of tolerance during these activities. Next, we consider these effects while considering a range of 10 different standards with 10 different quality relationships to our sensor target. I want to start by modeling my sensor data in column A as the sensor responds to these initial conditions and starts producing data. Feel free to pause this video at any time and follow my path exactly in your own blank Excel sheet. Here are all the steps necessary to populate column A with Monte Carlo simulations of our sensor data. The value for the mean that I selected here just portrays the results of an average of many repeated attempts to measure anything like temperature or pressure. But for you, it could be the mean of any measured parameter that's critical to your process delivery. In my example, that parameter has an arbitrary value of 5, but it could be any value. Units don't even matter here. I picked the standard deviation that you can see because I happen to know that 3 times this particular standard deviation, otherwise known as 3 sigma, still will enclose about 99.7% of all the variation that we're going to expect to see when we calibrate this particular normally distributed data source. You can model the variability of your particular data source as you see fit by controlling the size of the mean and the standard deviation, or you can just pick another distribution altogether. These two parameters are all that's needed to specify any normal distribution. Column B is where a lot of the Monte Carlo action is going to occur. This is where we're going to use different iterations in successive worksheets to mess with our standard and watch how the resulting disturbances change our risks and our assurance. We're going to saddle the standard with bigger and bigger out of tolerance findings, which will increase its actual variability as opposed to the specified variability contained in its tolerance. However, I suggest that we should begin by studying first a model using a perfect standard, even though that's unrealistic. It's very easy to do that in Monte Carlo by just populating every cell in column B with a 5. In terms of the model, this indicates that the standard perfectly duplicates the calibration environment every single time as we measure and record the sensor's response. This will allow us to establish a baseline for the way that the sensor and the standard interact in a perfect world. In fact, repeating 5 in column B also implies that we're pretending that our standard as well as our environment has no uncertainty and no variability. But it's still a good way to work out the kinks, test drive our approach, and ensure that all the equations we're using produce reasonable results in each of the columns. Next, in column C, we extract the absolute difference between A and B using the simple formula that you see right here. In column D, we populate each cell with the identical tolerance for the column A sensor because we need it to make a calculation. Try copying 0.5 to each row in D as a reasonable starting guess for the sensor's tolerance. In column E, we subtract the value that we found in C from the fixed tolerance in column D using this simple equation that you can now see on your screen. Column F is the column in which we toss the crucial decision rule. This rule will trigger recalibrations called for in some rows depending on the interaction between our Monte Carlo simulated data and our decision that we define. Now, here it is right here. Remember that recalibrations have a ton of risks for our enterprise because we may have already shipped product to our customers before we get the first hint that the calibration standard we used might have been out of tolerance. Now feel free to recreate any other decision rule that better reflects the way that you do your business. In column G, we count the actual number of resulting recalibrations caused by our rule using this simple formula. That's it. You've just modeled a calibration scenario using a perfect standard. In a perfect world, the resulting recalibration number should stay very close to 0 depending on your sample size. Now, I would suggest that you immediately title this worksheet tab with something like perfect or whatever else you want to call it. Next, you copy and paste this entire perfect worksheet into the next blank worksheet. Don't forget to immediately change the copied worksheet tab title to something else before you forget which is which. I suggest that you call this second worksheet 10 to 1. You may discover here that Excel will not allow colons in worksheet tab titles. Now go to column B of this 10 to 1 worksheet. Change the perfect 5 that you find there to 4.95. Why? That's because by doing this, you're modeling the first calibration scenario in which you get the news subsequently that your standard may have been actually reading 4.95 when it indicated 5 during the calibration. Also, 0.5 divided by 0.05 is 10 to 1. So this is a rather small deflection from a perfect standard. Of course, the key question remains, so what? What if we found later that when we thought the calibration conditions were exactly 5, they were actually closer to 4.95? The best way to answer that question is to keep a very close eye on the recalibration counter. When that count increases significantly from your first perfect state, then you also know that your risks are increasing significantly. Next, copy and paste the perfect sheet again. Label this tab 9 to 1. This time put 4.94444 in column B instead of 4.95. This sized offset in column B represents a 9 to 1 relationship between the standard and the sensor. In each successive worksheet, you add a new decreasing amount in column B that represents greater and greater offsets resulting from your out of tolerance. Eventually, you're going to get down to a cell value of 4.5 for column B, which also reflects the tolerance of the sensor and represents a 1-to-1 relationship between the sensor and the standard. You've reached the end of your road. Copying and pasting the first perfect template saves a ton of retyping. It also means that in each iteration, your column A data provides the same test for each scenario because it's the same exact data copied over and over again. Repeat this until you have modeled a spectrum of 10 ratios and gathered 10 very different numbers of required recalibrations. Ideally, you're going to see what I did, which is that there's very little difference between a 10 to 1 standard and about a 6 to 1 standard in terms of the number of recalibrations required. But below 4 to 1, you should see a rapid, explosive, non-arithmetic increase in the number of required recalibrations. This result is what validates the 4 to 1 calibration rule of thumb in the first place. Lastly, let me repeat my overall theme for emphasis. Monte Carlo is a powerful alternative in a case like this in which there is no real-world data source in existence that could ever possibly supply the insights that you just gathered in the last hour while you made these worksheets for the first time. Thanks again for watching this pair of videos, and I'd be delighted to hear the work circumstance to which you applied this concept and how it worked out for you. In the meantime, see you later, and thanks.